Duty?
Sure.
You've got one free homework exemption problem for the semester.
Literally racking up. Wait, this is for camera duty.
For camera duty,
Oh my
yes.
god.
Yes.
I've already got like 12 free.
Alright.
I've just two.
Alright, are you ready? So what we're going to start off today with is linear approximations. And hopefully you've seen something about linear approximations in Calc 1. So in one dimension, we have f of x is approximately equal f of x naught plus f prime of x naught, x minus x naught. So this is where you start, this is how fast you're traveling, and this is the amount of time you travel. So what we're doing is we're taking a complicated function and we're approximating it with a straight line. This is one of the greatest powers of calculus. And maybe later in the semester I'll show you some applications like the birthday problem where this is wonderful for getting the right answer. In two dimensions, f of xy is approximately f of x naught y naught plus df dx at x naught y naught, x minus x naught, plus df dy at x naught y naught, y minus y naught. So this is very similar to what we have in one dimension. If you go back and instead of calling this f of x, which it's only approximately equal, if you look at just the right-hand side, what kind of object is the right-hand side? What geometric object is constant plus constant times x minus x naught as x varies? This is the equation of a line. What is this the equation of? This is the equation of a plane. So all of our stuff about tangent planes, all of our stuff about planes, this is why we care about them. It's the generalization of a line. If I had 3 variables, I would just add a df dz. If I had 4 more variables, I would start using, df dx1, df dx2. So we've talked before about why the tangent plane works. Let me give you an approximate proof. And this is a very common technique. Start here at x naught, y naught. Move to the point x naught plus delta x, y naught. And then move to the point x naught plus delta x, y naught plus delta y. So I want to move from my point x naught, y naught to a point that's pretty close. So my point xy is this little distance away. How much have I moved? I've moved delta x in the x direction, I've moved delta y in the y direction. And the idea is if delta x and delta y are small, if I haven't moved that much, the tangent plane should be a really good approximation to the function, just like the tangent line was a really good approximation to the function. One way to derive this is to basically do the tangent line multiple times. If I go from here back to here, which variable is changing, which variable is not changing? Yes?
Y is changing and X is not.
Y is changing, X is not. So using the tangent line from here to here, let's go backwards. We would get f of x naught plus delta x, y naught plus delta y is my starting point. F of x naught plus delta x, y naught plus df dy at the point x naught plus delta x, y naught, delta y. That's what I get if I use the tangent line to approximate this point with the value of my function here. Now all I have to do is use the tangent line to approximate this value with the value here. Why don't I worry about approximating this? I'm evaluating this at x naught plus delta x, y naught. I want to evaluate it at x naught, y naught. So if I use the tangent line again, I would get approximately equal to f of x naught, y naught plus df dx x naught, y naught delta x plus df dy x naught plus delta x, y naught delta y. I don't want to evaluate this at x naught plus delta x. I want to evaluate it at x naught, y naught. Why can't I just say screw this and just drop the delta x? So why can't I just drop the delta x? Well, let's look at what happens when I look at my approximation with my tangent line. I take my function, it's where I stop, plus my derivative times how much I've moved. The contribution of this piece already has a delta y. When I approximate it, I could play the same game as before. I could say df dy at x naught plus delta x y naught is going to be df dy, and then I take the derivative of this with respect to x at the point x naught y naught delta x. So if I try to approximate this with a tangent line, it gives me a delta x. When I put that in here, I've already got a delta y. I'll have a delta x, delta y. If delta x is small, if delta y is small, what can you say about their product? Damn, no, it's more than small. It's damn small. It's extremely small. Some kind of profanity here. Damn small is a mathematical term. It's technical. Okay? It is insignificant next to delta x and delta y. Delta x, delta y, that's a second order small term. So to first order, we're not going to see differences like that. Okay? So that's why this is a really good approximation. You can just consider the succession of points like this. And this is a justification for why this does such a really good job. Okay? So again, this is the formula that we use. It's the tangent plane. And we say that if our function is differentiable, the tangent plane does a really good job. This is a way to see why it's coming. We're basically just applying the definition of the tangent line twice. Okay? Any questions about this? So notationally, we often write the following. So we have df equals triangle f. Okay, I'll do it at the point x naught. Is triangle f at x naught is gradient of f at x naught. And you can even write it as, df dx1 at x naught dot 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 df dxn at x naught. Or some books prefer to write d1f at x naught dot 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 df with an n subscript x naught. Why do you think we like to put these? Well, we use the letter d for derivative. And so rather than writing d by dx1, d by dx2, some people like to just write big D. For formatting purposes, it's sometimes a little bit nicer. And they call this the gradient vector at x naught. And we get the following approximation. F of x is approximately f of x naught plus the gradient of f at x naught dotted with the vector h, where x is x naught plus h. So we're using h to represent small little changes. So I start off with the vector x naught. Here's my x naught, and I move a little bit to some point x naught plus h. Think of h as a small amount of movement. This is one of the reasons why we like the dot product. It becomes a very convenient way of writing what's going on. Before we had df dx1 times the change in x1 plus df dx2 times the change in x2. That's exactly what we have here. When you look at this dot product, the gradient of f at x naught dotted with h is equal to df dx1 at x naught times h1 plus dot 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 plus df dxn at x naught times hn. Okay? So this tells you, if you know how much you've moved, approximately how much you've changed. This looks a lot like our equation for a line. All we've done is we've put vectors on things. So the way the derivative changed is our derivative in n dimensions is now a vector with n components. There you go. Our movement is now a vector. There you go. How do we have two vectors combine? We have the dot product. that gives me a number back. I have to get a number. Think of it as this is my temperature on the surface of the Earth. If I move a little bit, what is the change in temperature? Okay. Any questions about what we have here? So this is the tangent line, tangent plane. Okay. What I want to do now is I want to do an example, which is, I will do the same one that's either in the video or the notes, just to make things nice and to give you a sense of how well this formula can do. So we will try to approximate a function involving square roots. And you've hopefully heard me argue numerous times I don't like functions of square roots. So let's take example f of xy equals the square root of x squared plus y squared. What is f of 3.1, 4.9? Okay? I think only once in my life have I really used this. I was at a car deal and I was preparing notes, I think a year or two ago for this class, and my phone was so old it didn't have a calculator. And so I needed to approximate something, so I actually used stuff like this in Newton's method just to get the lecture done. Normally I don't use this to approximate functions, but I do use this to get some sense of the behavior of things. And so for something like this, no, but how many of you have heard of the birthday paradox, or the birthday problem? This is a great way to solve something like that. If time permits later this semester when we get to sequences in series, we'll do the birthday problem. So if I'm going to do this, I want to evaluate this function at the point 3.1, 4.9. I need some point close to 3.1, 4.9 where I can evaluate the function. This is not an important example. This is a cooked up example meant to be nice. Can you think of any point near 3.1, 4.9 where you can figure out the value of this function? Yes.
3, 5.
3, 5. Oh dear, did I make a typo? 3, 5 is not a good point, actually. Oh dear, I have made a really bad typo. What should we do with a really bad typo? So the problem is if we put in 3, 5, I just realized right now, oh dear, what happens if we put in 3, 5? What do we get?
20, radical 24.
We get radical 24. Do we know what radical 24 is? Do we know what radical 24 is?
2 radicals.
I'm sorry?
2 root 6.
2 root 6.
Radical 24.
Well, let's see, it's going to be 25, it's going to be radical 29.
Oh, whoops.
Wait, 3 is squared is
3
9,
and 5, yeah.
5 squared is 25,
34.
radical 34.
Whoops.
Right. Alright, so let's change the example. What should I put instead of 3.9? Alright, let's try this. Alright, cooked up example. Why am I choosing 3.1, 3.9? Pythagorean triplet. I'm trying to go, the 3, 4, 5. I think I was mixing this up with the 5, 12, 13. 5, 12, 13 is another nice one. So if we take x naught and y naught to equal 3, 4, then f of x naught and y naught is going to be 5. So we have a really good value. And so when we actually take the derivative of this function and all of its partials, they're going to be very easy to evaluate at the point 3, 4. And that's why I want this. So df dx is going to be 1/2 x squared plus y squared to the minus 1/2 times 2x. And so again, this is a good way for us to just practice our partial derivatives. I'm taking the derivative of this with respect to x. I have something to the 1/2 power. The 1/2 comes down. So df dx at the point x naught, y naught, the 2's cancel. What's x squared plus y squared to the minus 1/2? That's just going to be 5. 1/5, so 5 comes down below. And then I just have x naught up top, which will just be 3. So df dx at the point I care about is just going to be 3/5. df dy is going to be 1/2 x squared plus y squared to the minus 1/2 2y. df dy at the point x naught, y naught will just become what? So this would just be 4/5. Alright, so the approximation would be f of 3.1, 3.9 is approximately f of x naught, y naught plus df dx at x naught, y naught. What's the change in x? How much is x changed by? 0.1 plus df dy at x naught, y naught, and how much is y changed by? I'm sorry? Not 0.1, close, but not 0.1. Negative 0.1. I deliberately chose 3.9, well, I accidentally chose 4.9, but I wanted to choose 3.9 to have y moving backwards. So y has gone down by negative 0.1. So I get my approximation is about 5 plus 4/5 times 0.1, which is 1/10, minus, plus, I'm sorry, the first one was 3/5. The next one is plus 4/5 times negative 1/10. So I'm going to get 5 minus 1/50. So I'm going to get 4.98. Okay? Amazingly, even though I wrote the wrong numbers in my notes, I actually calculated as if it was the 0.34. And so the actual value is f of 3.1, 3.9 equals 4.98197. Impressed or not impressed?
Impressed.
Impressed, right? When I tell you I beat the kids at the elementary school in tic-tac-toe, impressed or not impressed?
Impressed.
Impressed? Wow, you guys are impressed easily. Alright. Why is this good? Why is this impressing you? Other than I control your grades. Actually, you control your grades. Now, you learn the material and I will not flunk you. Why does this impress you? Why is this good? Why do you think this is good? Yes?
Because it allows you to get really good estimates of really complex functions. Like,
Simply.
But
why is this a good estimate? What makes this good? How much am I off by?
0.002.
0.002. And my movement is of size 0.1. So my error is roughly of size distance moved squared. So I've moved 1/10. My error is like 1/100th. Okay, it's a little constant times that. That constant's going to involve the derivatives. We'll see a lot more of why this is true when we get to Taylor series. But this is really good. In terms of losing information, I've only lost on the order of about 1/100. I've lost about the square of how much I've moved. That's phenomenal. That's incredible accuracy at very little work. Right? If you would like, if you get bored later today, either in my class or in another class, try calculating the square root of 3.1 squared plus 3.9 squared directly, multiply everything out, try to do approximations for the square roots, try guess and check of numbers to find out exactly what it is, and see how much work you have to do to get that. This is not much work at all. Okay? So this is one of the powers of linear approximation. Okay? Any questions on this? So this is one of the reasons why we love calculus. With very little work, you can get an incredible approximation to something. What I want to do now is I want to talk a little bit about approximations and how you can use this for a variety of problems. How many of you have ever seen Star Trek: The Wrath of Khan? I know it's not that many. The original, not the bad remake. Star Trek: The Wrath of Khan is the first movie to involve fractals. I think I showed you a video of fractals earlier this semester. Okay, we zoomed in on the Mandelbrot set. Okay, we're going to play some other games with fractals today. And we're going to use linear approximations and shampoo conditioners to figure out how to solve equations. Right? This is what science is about. Science is about, sorry, I'll stay over here. You're a good sport. Science is about solving equations. Okay? You give me an equation, I want to find the answer. So here's two methods. Method one is called divide and conquer. And it uses the intermediate value theorem, assumes f is continuous. And the idea is the following. For simplicity, let's assume I look at the interval 0, 1, and let's assume my function is positive over here, and my function is negative over here, and it is continuous. If my function is continuous, what do you know? Yes? How many times? Almost.
An odd number of times?
So if you have a multiple 0, you count that twice? I could have something that comes down like this as a double 0 and then goes like that. So if you count that double 0 as 2, then yes, it will cross an odd number of times. We know it crosses at least once. There is at least one root of the function in this interval. And so the intermediate value theorem allows you to find it, assuming you can just evaluate the sign of the function. What you do is you divide the interval in half. There's three possibilities. My function is 0 here. Yay, I win. It's positive or it's negative. Do you want it to be positive or negative?
Positive.
Positive. Does it really matter?
No.
No. So let's say it's positive here. I now look somewhere between 1/2 and 1. I look at 3/4. What's the value of the function here? Negative. Okay, we'll do negative this time. So now I have to evaluate halfway between 1/2 and 3/4. So that's going to be 5/8. And you just keep playing this game. This is called divide and conquer. Every time you iterate, you have the window where you don't know, you have the size of the window where the root lives. So if you do this once, you have it. If you do it twice, 1/4. If you do it 10 times, what does the size change by? 10 times decreases by what? So each time I have a factor of 1/2, I do it 10 times. What should it be? You can tell me in terms of just 2.
1/2 to the 10th.
1/2 to the 10th. And 1/2 to the 10th is approximately, well, it's actually 1/1024, so that's exact, but that's approximately 1/1000. And this is why the computer scientists sometimes cause issues because of how they have adopted the different, classical words like megabyte and gigabyte. I don't remember if this is Latin or Greek, but whichever one you're using, mega to giga is supposed to be a factor of 1,000. Well, for computer scientists, 2 to the 10th is almost 1,000, close enough. So if you ever watch a hard drive copying information and talks about how many megabytes have been copied, all of a sudden when it gets close to a gigabyte, it's like 995 megabytes, 996, and then it changes like 0.99 gigabytes. That's because 1 gigabyte is 1,024 megabytes. So essentially what this means is every 10 times you do this, you gain 3 decimal digits of accuracy. So to get 6 decimal digits of accuracy, how many times would I have to do this? 20 times. That is a lot. Okay? Have I shown you how to use this to guess someone's birthday? So for kids aged between 5 and maybe 10, this works well to use them for a little bit. I need a volunteer. Alright. You either have to think of your birthday or think of a random day in the year. Do you have it?
Yeah.
Okay, if I'm wrong, you have to tell me earlier or later.
Okay.
I will guess your date in 10 questions or less.
Okay.
Alright, what's my first guess?
January 1st.
No.
July 1st.
July 1st, June 30th, something like that. Guess halfway in the year. So is it July 1st?
Earlier.
Earlier. I'd rather do July 1st because there's February only with 28 months. So with my first guess, here's July 1. I know it's now earlier. Now where do I guess?
halfway.
Halfway. I'd say April 1st.
Later.
And then since this is being recorded, I'll stop here. But you know, keep doing this, right? Well, actually, it's almost impossible for someone not to find all of your confidential information with a quick web search.
Exactly.
I know, but I'll still stop just in case. This is the power of binary search. It's very easy to do. And because 2 to the 10 is 1024, and there are only 365, 366 days in the year, I will do this in 10 questions. Do I really need 10 questions? No, this gives me a little bit of a margin of error when I make mistakes. Okay? This is the power of divide and conquer. All I need is my function to be continuous. What am I ignoring? What would be wonderful to use? What class is this? Calculus. What would you like to use?
Calculus.
Calculus. When we did the method of least squares, what did we use in the method of least squares?
Calculus.
Calculus. We didn't use the second method to measure error because that method, you know, while it was maybe nicer from a philosophical point of view, we're not philosophers, we're mathematicians. We need to implement these things. And so what we want to do is we want to have some way to use all the tools and techniques from calculus. So what I want to do now is I want to show you Newton's method. So this was the topic that switched me from mathematics to physics. I'm sorry, from physics to mathematics. You know, when I just saw how well Newton's method worked. Okay? Newton's method is a wonderful application of the tangent line. Of course, I'm doing it for function in one variable. I could do Newton's method in several variables. This is enough to really show you what's going on. So let's say f of x is x squared minus 3. And I want to solve f of x equals 0. What is the solution? I'm sorry?
-3.
No.
Square root of 3.
Square root of 3. Anybody with a calculator want to tell me approximately what square root of 3 is? You know, just saying square root of 3, you've given it a name. But you know, in terms of computing things, square root of 3 is not that pleasant. So what is the square root of 3 equal? 1.732. Who can pop up more digits? Right. We'll stop with that for a moment. Alright. I want to show you how Newton's method works. Here's the square root of 3. I'll move it over a little bit because of where I fit. Here's the square root of 3. And the idea is the following. Let's take a nice guess for square root of 3. Anybody want to give me a nice guess for square root of 3 that's a nice number to work with? Doesn't have to be that good.
1.5?
No. 2. Much better guess, right? 2 is much easier for me to work with. You have too much faith in my algebra. I've deliberately made mistakes today in the algebra to convince you I can't do this. Alright? That's known as reverse. Okay. So let's guess x naught equals 2. So here's how Newton's method works. So I come to the point 2, and I draw the tangent line at 2. So I've got the point here, 2 f of 2, and the slope is f prime of 2. So this is a great way to review tangent lines. So what's f prime of x? It's going to be 2x. So my point is going to be 2 f of 2. Slope is f prime of 2. So the tangent line is y equals f of 2 plus f prime of 2 x minus 2. Or y equals f of 2 is what? F of 2 is?
6.
I don't get 6.
I mean,
So I plug in 2 for f of x.
1.
1. So I get 1 plus f prime of 2, which is going to be 4, times x minus 2. Does the tangent line equal the function everywhere? No, it equals the function at one point. Alright, let's forget about the fact that it doesn't equal the function everywhere. Let's just replace the function with the tangent line. And let's just follow the tangent line down and see where the tangent line hits. So we can solve for where the tangent line hits the x-axis. Hits at y equals 0, right? So we need 1 plus 4 x minus 2 equals 0. Therefore, 4x minus 7 equals 0. We'll call this point x1. Therefore, x1 equals 7/4. So our second guess is x1 equals 7/4 is 1.75. How good of a guess is this?
It's pretty great.
Pretty great. So, if nobody has calculated the square root of 3, I do have it here. 1.7320508. 05, I think 08. How's that for an approximation of the square root of 3? One step. I've got 1.75 rather than 1.732. Alright. What are the instructions on shampoo or conditioners? Yes, lather, rinse, repeat. Right? That's what we do here. Once we've done this approximation, we now have our next point. Now we play the same game as before. This was x0, this was x1. We now come up to the curve, and we find our new point. And we draw the tangent line through that point. It's not a coincidence that when I'm drawing it, it's this close. It's phenomenal about how well it does. When you do this algebra again for the next point, you get the following. 97/56. Okay? You get 97/56, which is going to be 1.732, 1428. That's not bad. When you do it again, so this was x2, x3. Okay, I can switch actually and put it on the board. I'll put it on the board. So the initial guess was 2, second guess 1.75, dramatically coming down, 1.732. Difference is small. Term 3, 1.7320508. Term 4, 1.732050807568888. The difference to square root of 3 is dramatic. 10 to the negative 18. After 4 guesses. If you wanted to do it one more time, the error is 10 to the negative 37. So let's look at the errors. 10 to the negative 9, 10 to the negative 18, 10 to the negative 37. What do you seem to be noticing? What doubles? Before, when we did divide and conquer, the error went in half. Here it's the exponent that doubles. Every time you apply Newton's method, you double the number of decimal digits you have. Okay? This beats the hell out of divide and conquer. It is not even close. You know, try doing divide and conquer to estimate square root of 3. After just one iteration, I've got 1.75. After 2 iterations, I've got 1.73214. You know, the correct answer is 1.73205. You know, after 3 iterations, I'm at 1.732050881 versus 1.732050807. The error is incredibly small. So why do you think Newton's method does so much better than divide and conquer? It uses the derivative. We use more information. So not surprisingly, when you use more information about your function, you should be able to do more. Okay? And that's the glory of calculus. So since I've already shown you some movies about fractal sets, I'm going to just show one movie today. In this example, we're looking at the function f of x is x squared minus 3. So how many roots are there? How many roots are there to x squared minus 3? 2. So the danger is, how do I know which root I'm going to go to? Am I going to go to square root of 3 or to negative square root of 3? So, in an advanced math class, you would analyze this algorithm and see which root would it converge to. For quadratics, it's not so bad. What might happen with a cubic? How many roots would you have with a cubic? What if we looked at x cubed minus 2? How many roots? 3. So then the question becomes, which root do you go to? If life were good, which root do you think you should converge to? I'm sorry? Well, you've got some function, let's say the 3 roots are here, and if you start near this bottom point, which root do you think you should converge to? The nearest one. You should always converge to the nearest root. Wouldn't that be a wonderful thing for an algorithm to have? Alright, so I apologize, I was loading these up late last night. I can't remember if this is one of the ones with the cheesy music or not. People seem to find cheesy music helps. So what we're doing here is we're coloring the points in the complex plane. There are 3 roots. This is looking at x cubed minus 1 or x cubed minus 2 equals 0. Green are all the points that zoom in to the root at 1. And then the red is the next root, the next one. These roots are symmetrically distributed. Right. So this is one of the examples of a fractal. A fractal is extremely sensitive to initial conditions. This should disgust you. Right? You know, I'm closer to this root if I'm right over here, but I could somehow zoom in and get to that one? So what I'll do is I will play a little bit of the movie and it's going to zoom in. And so, okay, this is not one of the ones with cheesy music. But this is zooming in is what's going on. So, we've zoomed in. This is the incredible dependence on initial conditions. Right here at this point, wild things are happening, and small little tweaks, and you can converge to any of the roots. So this leads to the questions about stability of algorithms. What class will you take after this?
Linear algebra.
Right. Stats 201 is also acceptable. But in linear algebra, you will calculate what's called eigenvalues of matrices to try to understand how these transformations work in the real world. And the question is, how stable are your algorithms? If you do this crudely, you could have a polynomial degree 100 where you're trying to find roots. Small little mistakes could move you to the wrong place. So here, just as you're zooming in, I mean, it's incredible the degree of self-similarity. As you keep zooming in, you see the same behavior again and again. I think there is a requirement that whenever you talk about fractals, you have to do something with the Mandelbrot set. And so, I'm not quite sure why the volume is not working. I don't never mind. So here's zooming in on the Mandelbrot set. Interesting, speed this up too. And so just an incredible amount of self-similarity as you're zooming in. And you keep seeing the same behavior again and again and again on small and small scales. This is extreme sensitivity to initial conditions. My computer should be running faster than this, so to just help it out, I'll just, just manually force it, zoom in a little bit. Keep seeing the same figure as you zoom in. And I'll post these videos online. As you keep zooming in, you see the same behavior. It is extremely difficult to actually do these calculations because they're so sensitive. And in fact, in the video for the class lecture, I go through what's called Horner's algorithm, which is a better way to evaluate polynomials. You need something like that if you want to do evaluations like this. Alright, so again, this is what converted me from physics to mathematics, is just seeing the incredible power of algorithms like Newton's method, how well it could handle things like this. And you're just seeing as you keep zooming in again and again and again, this same shape, zoom in a little bit more, zoom in a little bit more, there it is again. And when you think of how small of a scale this is, it's incredible. In Star Trek II, The Wrath of Khan, one of the greatest science fiction movies of all time, lots of great quotes, the Genesis torpedo, the special effects for that were done using fractal geometry. It's one of the first examples of the use of fractals. And so evaluating stuff like this is extremely difficult. All right. Any questions about fractals? So in some sense, these have been two of my favorite lectures, the ones we've just had for the past 2 days. We've seen applications of calculus. And again, in a class, it's always, why am I taking this? Why am I studying this class rather than something else? What can I do with it? Well, here are some things you can do with calculus. This is one of the reasons why we care so much about stuff like this. Right? We can approximate complicated functions very well. We have a few minutes left, and so what I want to do is I want to use the remaining time as a way to introduce the chain rule. So the chain rule is, I think, the worst of all the different rules from calculus to remember. Okay, so chain rule. So let's let a of x equal f of g of x. Then a prime of x is f prime g of x times g prime of x. This is probably the rule people get wrong the most. Most common mistakes. Mistake number one, and again, it's really close as to which mistake is the most common, is to have f prime of x, not f prime of g of x. You have to remember where to evaluate your function. Okay? For example, let's say f of x is the square root of x, and g of x is x plus 4. Now let's do x plus 6. Doesn't really matter. Look at x equals -2. What is f of g of -2? Well, g of -2 is 4, so this is f of 4. And what's f of 4? 2. Everything is fine. But f prime of x is 1/2 x to the -1/2. What's f prime of -2? That's 1/2 the square root, 1/2 1 over the square root of -2. The square root of -2 is not a real number. Okay? This is the danger of evaluating my function at a place where it's not defined. I am never evaluating f at the point x in this problem. I'm evaluating f at g of x. Okay? This is one of the most common mistakes people make, is they drop where the point is. They drop the g and they try to evaluate the function at x. In a lot of problems, you won't get a mistake like this, but you will get the wrong answer. You'll be evaluating the function at the wrong point. So that's mistake number 1. Okay? What do you think mistake number 2 is? What do you think people forget? Yes?
You forget to add g prime of x.
Yes, they forget the g prime of x. I've told you mathematicians are lazy, and mathematicians can basically do 2 things. We can add 0, and we can multiply by 1. What's the derivative of x to the n? You've all been warned. You can give it to me correctly. The derivative of x to the n.
nx to the n minus 1 times the derivative of x.
Excellent. And what's the derivative of x? 1. So when you write xn and take the derivative of that, there's a 1 floating around. How many of you are going to write times 1? Okay, if so, you have issues, you need to talk to me, okay? You don't want to keep writing the times 1. The times 1 is understood. There's no reason to keep writing the times 1. But when you're trying to think about how things generalize, it's exceedingly important to remember there is a times 1 there. And so this g prime of x is extremely important. Okay? The g prime of x is absolutely essential. Okay, so this is the classic chain rule. On Wednesday's class, we will prove it. I will give you an example now of why we care about the chain rule. So any questions about this before we do the application? How many of you have heard the inverse function formula? So the chain rule allows you to pass from knowledge of one function and its derivative to knowledge of another. So assume a of x equals f of g of x equals the function x. So f and g are inverses. What does a prime of x equal? There's two ways to compute it. Somebody give me an easy way to compute a prime. A prime of x equals?
1.
1. It's equal to x, so it's just equal to 1. But it's also f prime g of x times g prime of x. Therefore, g prime of x equals 1 over f prime g of x if f of g of x equals x. This is a beautiful result. If you know one derivative, it allows you to get a related derivative. So for example, if I look at a of x is e to the natural log of x. So I'm raising e by the number of powers of e I need to get x. What is e raised to the number of powers of e I need to get x? E raised to the number of powers of e I need to get x is just? Not 1. I'm raising e by the number of powers of e I need to get x. It's just x. So what this tells us is, therefore, the derivative of the natural log of x is just 1 over f prime, which is going to be the exponential function again, evaluated at g of x, which is 1 over x. So if you know the derivative of e to the x, you now know the derivative of natural log. I'm not going to go through the details, I'll leave this to you. I could give you a of x is the sine of arc sine of x. So what is the sine of the angle whose sine is x? X. You can now figure out the inverse trig functions. The difficulty is you need to express sine of arc sine or cosine of arc sine in terms of x. I'll leave that for you as a nice exercise. Maybe we'll talk a little bit more about it on... Oh, we've got 1 minute. We can do it for 1 minute. Here's arc sine of x. So what does it mean? I have some angle theta, its sine is x. So if the hypotenuse is 1 and this is x, right? Then this would be 1 minus x squared square root. Because by Pythagoras, this would now give me a right triangle. So arc sine prime of x is 1 over sine prime at arc sine of x. What's the derivative of sine? So I have 1 over cosine of arc sine of x. Well, what's the cosine of the angle whose sine is x?
Adjacent over hypotenuse.
Which is going to be square root of 1 minus x squared. So square root of 1 minus x squared. There is your formula for the derivative of arc sine. As a nice exercise, find the derivative of arc cosine, find the derivative of arc tangent. Arc tangent is actually extremely important in calculus. Arc sine and cosine not so much. But arc tangent matters. Right? This is the power of the chain rule. So we will see a lot more on this later. Okay? So again, I'm hoping today you saw some of the applications about what we can do with mathematics, and the motivation will carry you through the painful lecture that will be Wednesday. Okay.